Okay, hello class. Last chapter, chapter 3, book 3.5. So we are going to actually come upon something that we've seen before, but we're going to deal with it in much more depth. So vector fields we saw in book 3. When we talked about the gradient, we thought about the gradient as a vector field. So we'll return to that, but we're going to add quite a bit more this time when we think about vector fields. Beyond just R2, we'll go to R3 and beyond. We'll add ideas of flow lines, how much work is done by a vector field. So we're going to start off though in this first video, just getting some vocabulary and some computational skills. Okay. So back in book 3, we were dealing with multivariable functions, functions of two independent variables affect a third one. So we have an explicit functional form, something like this. Hopefully you recognize the shape. We have one has a positive, one has a negative, makes that saddle surface, hyperbolic paraboloid. And we're going to compare that with this function over here. Capital F is the notation we're going to use when we talk about vector fields now. So these were our explicit functional form. We're now going to have a new type of function. And in this case, you enter an x and a y, and it spits out a third variable z, which is your height. Here, you enter an x and a y into this function, and it spits out a vector. So this is why we're doing, in book 3.5, it's vector functions, vector calculus. And this time, again, we've kind of seen something like this before. And so here's what we did when we took gradients over here, or took our partials, partial with respect to x, let's see, negative x, partial with respect to y, put those in a vector that we called the gradient of our function f, this upside down triangle, put those two things together. And so we're just saying this is something we've seen before, but more generally, we're going to use the capital F to talk about vector fields in general. Here, this was a vector field that was a specific type of vector field called the gradient vector field. And we're going to return to those a few times this chapter. Okay. But the first thing we're going to do when we talk about general vector fields, they don't have to be attached to an explicit function, which then we took the gradient, which creates a vector field. Just in general, we might be given a vector function that creates a vector field. And so what this is, at every point x, y, we can actually plot a vector. And so we're going to do this. I'll do a few, and then we'll finish up the whole field, and then finally we'll use tech tools that'll help us do this as well. So I could be doing like f of, let's say, 1, 1. That's the vector negative 1, 1. F of 2, 2, let's say, negative 2, 2. Those are a few where now when I plot them, the vector field, oh, by the way, this is an R2 vector field, right? Because it creates a two-dimensional vector on the outlet when you're done. You input two independent variables, x and y, that are a point in two-dimensional space, and it'll output a vector. So when I graph f at 1, 1, I go to the point 1, 1. That's our input. The output is a vector, negative 1 in the x direction and 1 in the y. So pointing that way. At the point 2, 2, I start here now. I go negative 2 in the x, positive 2 in the y. I have this vector. And we can see this pattern, right? But those are just the few that I tried. There's infinitely many points I should consider. Maybe I want to try 1, 2. That'd be negative 1, 2. So at the point 1, 2, which is here, I'm going negative 1 up to, so a little steeper. Maybe I want to try 2, 1. That's negative 2, 1 is the vector. So I start at the point 2, 1. And I go negative 2 in the x and 1 in the y. So it would be like this. So we kind of get the sense that points over here in quadrant 1 are shooting up towards the positive y-axis, but let's see what happens in different quadrants. And so I'm actually going to pause the video and fill in some more so you don't have to watch me do these sort of basic computations here. And then Okay, so I filled in a few more, just again, plugging in points. Output is a vector, plotting those. I think I had one of them a little off, so I think I fixed that one there. But what we see again in the upper quadrants, we're peeling off and going towards the positive y-axis. In the lower quadrants, I only filled in a few, but the same idea. There's just a symmetry there. And so when you plot this for a grid of points, again, there's infinitely many points in the XY plane. So I could be adding some here and here, all sorts of other points. If I want to add a whole bunch more in, right, I could be checking there and there and there. But you just want to make usually a uniform grid at some number of points to get a sense of the action of the field. There's actually infinitely many places you could plot it, but you just choose a finite that gives you an idea of what's happening with the field. And so let me show you again a tech tool, because only the simplest ones will we do by hand. You can do some R2 ones, and even these get a little tedious. You can do some really basic R3, and we'll do one in a moment. But for the most interesting and useful and applied problems, you're going to use a tech tool that is doing this very thing. It's just plotting points. It likes that computation, it likes that TDM, and it goes for it. So let's go ahead and share the screen and go to our usual tool for Calc 3. So CalcPlot 3D. All right, so in this case, let me just show you straight from the beginning. Turn that one off. Let's go down here to our explicit functional form. So in book 3, we took things that z was a function of x and y. And so the one that we had on the board over here in the corner, -1/2 x squared plus -1/2 y squared, that creates this saddle surface. We've talked about that before. Were we to take its derivatives, put them in a vector, we get a gradient vector, which is exactly the same on the left side here, this gradient vector, or just ignoring that it actually came from an explicit function, you could have just started with a vector field here. And so to do that, and we've seen a little bit of this from book 3, in CalcPlot 3D, you select a vector field, and what shows up is an M, N, and P. Those are your first components. So CalcPlot 3D in most textbooks, the first component is M, the second one is N, and if you have an R3 field, the third one would be P. Since we only have an R2 vector field, we just set that to 0. And we enter the two components, -xy, turn this on, and it will show it, again, the R2 vector field lives, its vector field lives in the XY plane, which it shows it here, but it's in 3D, so why don't we just restrict it to 2D? So our usual orientation, the y-axis up, the x-axis. So again, we see what we have plotted. Our black vectors are their blue vectors. These vectors are at a grid of points. You can change the number of vectors you want to add. If you want some more fine-grained approach, you adding more in there. You can also, this button down here, use a fixed length for all vectors. So it just shrinks them so they have the same length, not necessarily unit length. We'll get to that also a little bit later. But this is sometimes useful because they can get really long. Sometimes if you're putting more in there. So again, there's some getting long, but had I added even more, maybe 5 vectors. A lot's happening, but if you fix the length, you can get a little bit more sense of what's happening. And we're going to often be analyzing, like, suppose this vector field represents something like it's the current at the top of a river, the flow, the leaf would drop down, and you could imagine a leaf dropping right here. What would happen and where would it go? Well, you would follow these vectors and do some vector hopping and get a sense of what would happen to the leaf if these little blue vectors represent the flow of water at the surface of the river. So sometimes adding more is helpful. Sometimes you want just fewer in there. And that's, again, looking similar to what we had done with ours. Okay. So that's an R2 vector field, but let's do another example. Again, we don't usually do these by hand when they get to be R3, but there are some basic ones that we can do. So let's look at a simple one that we can actually plot by hand. In this case, we're going to have 3 inputs, X, Y, and Z. Now let's say we just have this 1, 3, 0. So again, each of the components, m is a function that represents your first movement in the x and the y and then the z. We get 3 inputs, and now we get an R3 vector field. And the idea is to sketch it, get an idea of what it looks like, and then we'll use a tech tool to check that. This is a really basic one because the same thing's happening no matter what I put in for the point of interest. So maybe 0, 0, 0 at the origin, you still get the vector 1, 3, 0. At the point 1, 1, 1, the same thing happens, 1, 3, 0. So this is a constant vector field, a really simple one, which is actually why we can draw it. So if I try 1, 2, 3, I still get 1, 3, 0. And so in R3, we can start plotting these. At the origin, we go 1 in the x, 3 in the y, and none in the z. And so it would be something like this. And that would happen at every point. So even at this point over here, this would be the point, this was 0, 0, 0. This would be the point 0, 1, 0. It still moves in the same direction, right? Same thing from here. At the point 1, 0, 0, we still move. And we can fill these in all over the place. In higher planes, up here even higher. We're always moving like that. If we put a whole bunch of those together, again, we can see the movement is always going in the 1, 3, which would be what? If we're in the XY plane, that would be northeast. Okay, but let's go back to our tech tool. So the only thing that's going to change now, we will enter 1, 3. This also, the third component, 0, but we don't want to restrict it to 2D. Oh, I forgot to talk about you can scale the vectors by some amount. Like if they're too long, again, you can come up here and they're dividing it by like 7, just to get shorter ones. That doesn't necessarily fix the length, it just keeps the lengths relative to each other according to some scaling factor that you've chosen. Okay. Okay, one more thing on CalcPlot3D. So this is the 1, 3, 0 vector, but we have to be careful down here along the z-axis. So we decided to just put one set of vectors on the z-axis. So we really should watch what happens when we change that. Now they're adding 2, 3, 4. So you're actually now getting the view that was shown when we drew it by hand. We know that there's infinitely many vectors, but they're all pointing in the 1, 3 direction. They have no height z, so it's a set of, what is shown here is a set of planes at different z heights, but again, there's infinitely many. And so if this was now in 3D, let's say instead of a water flow, let's say this is airflow in a room or outside with the wind is always blowing across horizontally this way. So no matter what, say a leaf gets injected into the system right here, it's just going to go across this plane and move in the 1, 3 direction. So it's important again that you can change these different, if you got too much going on, maybe you want to back off the number of vectors in the x and y. As usual, you can change the views with your arrow keys, gives you better control. And again, scaling, these all have the same length, so it doesn't matter when I scale, you won't see any difference, but for other vector fields, that would be a helpful one to use. Okay, so a few more pieces and then we're almost done with this is vocabulary. So we need to talk about, I think we did talk about this, but unit vector field. That's a vector field where all of its vectors have length 1. Any vector field, just like any vector, can be normalized to make it a unit vector field. So in this case, if I just divided by the length of every vector, in this case, every vector has a length of what? Square root of 10. So if I took this and divided that whole thing by square root of 10, I would have normalized it now. Let's see, the other one we had up here, let's put the R2 vector field back. If I wanted to make it, force it to be, let's say, normalize the vector field The other one we had was f of x, y. Two inputs create an R2 vector, which was minus x, y. If I wanted to normalize it, maybe I'll call this one g of x, y. This is the same one, minus x, y, divided by the length of any one of these vectors, which is the sum of the components squared, the square root of that, so it would be x squared plus y squared. By doing that, again, you've taken one that was not a unit vector field and you've turned it into a unit vector field just by normalizing, by taking the length of a vector as you normally would. This would be a good thing to check, practice in CalPlot 3D is enter the original field. That was the one in R2 where we were going up the y-axis or down, funneling into the negative y-axis. And then just check, this will have the exact same motion, but the length of the vectors will now all be length 1. So do that. Good thing, pause the video and do that now and check it yourself. Okay, a couple other terms we need to know. So unit vector field, there's something called a radial vector field and a rotational vector field. A radial vector field sounds like its name is suggestive. Let's do one, squeeze it in here. The R2 vector field x, y is a radial vector field because its vectors radiate, they can either radiate away from the origin or towards. In this case, they're going to go away. So real quick, we'll go back to CalPlot 3D. We will enter x, y. We don't want to see all of them because it's just a 2D. Or we can say just restrict to 2D. And again, notice that they're all radiating away or had all the vectors been pointing towards the origin. That's another one, the gravitational field in R3 pointing towards the origin. That is a radial vector field. Again, think about the word radiate. They're radiating like rays of the sunshine. And then last one is rotational. And so an example of a rotational would be f of xy is y minus x. And let's just go ahead while we got the screen share and put that one. So y minus x, switch these, y. Right, it looks rotational, right? The action of the field, if this is a leaf landing in the river current, it's going to be spinning this way. So when the motion is rotational, you have a rotational field, it doesn't matter whether it's spinning clockwise or counterclockwise. We can have those in R3 as well. We'll think about ones that have a sort of helical motion that seem like tornadoes or clothes dryers. There's plenty of activities in this first part of chapter 3 of your book. So make sure you have your vocabulary down. The key things we want to be doing at this point is, can you plot a few by hand for really simple ones? Can you use a tech tool? Can you visualize the action of the vector field once you've used that tech tool or done it by hand? And can you normalize a vector field and make it a unit vector field? Okay, next time we're going to talk about flow lines. We sort of did a little bit here, but a flow line is when a particle is injected at a particular point in the system following its flow. It makes a line through the field. So we'll get to that next.